Hey, so today what we're going to do is we're going to derive and use the Maxwell-Boltzmann distribution function for an ideal gas. Now, I want to go ahead and warn you that this is pretty math intensive, so don't be afraid to pause the video, rewind the video, make sure that you understand what I'm saying, and then make sure to go through after this is over and be able to understand and derive all the math and the algebra that I'm going to be showing you and using, okay? All right, so to get started, remember that what you've got to do to get a number density for a distribution function is you're multiplying the volume times the density of states and times the distribution function, all right? So we covered that in the first lecture on the chapter. Now what we've got here for the classical particles in a Maxwell-Boltzmann distribution function is this Boltzmann factor, which will function as our f of e here in this equation. And remember that we derived that this was equal to e to the minus delta e over kt, where delta E is the energy difference between energy levels 1 and 2, and T is the temperature and K is Boltzmann constant, and that what this little Boltzmann factor gives you is the ratio of probabilities that these states are occupied at a given temperature T. So this gives you the ratio that of the probabilities of the occupation of state 2 versus state 1. And this is what we get when we use our Maxwell-Boltzmann factor. So this is our f of E for our distribution function. And now we're trying to get to the number distribution function n of e, so we also need the density of states, all right, which we have not yet derived. So that's the next thing that we're going to do. So what we're going to do is we're going to look at the density of states for a quantum particle or a gas of quantum particles confined in some volume. So this is what we're going to do. We're going to assume that it obeys kind of the three-dimensional infinite square well potential. So let me remind you of what the one-dimensional infinite square well potential is. Remember from Modern 1 that you have a quantum particle confined in a well. The potential is equal to 0 inside the well, and then outside the well the potential is infinite, so that it's confined inside this box. And what happens is, because of the wave nature of the particle, it forms a series of standing waves, and the number of bumps in the standing wave gives you the energy level that the particle is in at that particular time. And so the energy levels starting with n equal to 1 look like they do here in the drawing. You've got your one hump sine wave, your double hump sine wave, and your triple hump sine wave, and that is what's confined. And it's really similar to the solution for waves on a string when you have both sides of the string tied down. So it's a sine function, and it's sine n pi x over L, where L is the length of the well and n is the energy level. And then the energies associated with the energy level n, we showed in Modern 1, where h squared n squared over 8ml squared, where h is of course Planck's constant and m is the mass of your particle. Now we also discussed how if you move this over so that it's not just in one dimension but in the more realistic 3 dimensions, what you would do is you would assume that each direction is independent of the other, and you would just multiply the sine functions for each direction by each other. And so you'd have sine of n pi x over L times sine of n pi y over L times sine of n pi z over L. And then of course these a's here are just normalization constants that we can solve for later. Okay, so that was our quantum particle confined to a three-dimensional square well. And this is actually a really nice analog for a gas of atoms, all right? So if you're assuming you have an ideal gas, you've got monatomic atoms there, just one atom, confined inside a box. Okay, now we're going to assume that it's a cube for now, but the idea that we're going to derive here for our density of states could be extended to a sphere or a cylinder or whatever shape that you want to confine your ideal gas to. So the shape of the box is really sort of immaterial. We're just going to use a cube for convenience, all right? Now, for an ideal gas, just like the particle in the infinite square well, you can assume that the potential inside the box is zero. And this is because the particles only interact with one another very weakly in the ideal gas molecule, and they're so light that you can kind of neglect the effects due to gravity if there are any. So really, your potential inside the box is zero, but there's no way that an ideal gas particle can escape, for example, a container like this one. It's not going to be able to tunnel through the wall, and so you can assume that as long as the seal is good on your container that they're not going to escape. So an infinite square well potential is actually a really good model system for this one. Okay? Now, we derived, or I showed you and reminded you, what the energy levels were like for a particle confined to a one-dimensional box. Now, for a three-dimensional box, the energies look very much the same, except you have h squared over 8ml squared, and then times nx squared plus ny squared plus nz squared. And remember, we covered in Modern 1 degeneracy and all that kind of stuff. Okay? So the only change that I'm going to make to this is I'm going to say, okay, let's assume that our quantum number n squared is equal to the sum of the squares for the independent directions. So here I have n squared is equal to nx squared plus ny squared plus nz squared. All right? Now, in order to figure out our density of states, which is the probability or the number of states that are available per unit volume, okay, then what we're going to do is we're going to move this over into so-called energy space, okay? Now, energy space, or any other kind of phase space, you might hear people talk about phase space, is really nothing more profound than, instead of visualizing your particle plotted relative to its location, now you're going to plot for your particle what the energies are, or maybe what the speeds are, or whatever other kind of a parameter that you're interested in. And then you're putting it in energy phase space, okay? So here, I'm actually putting my particles in quantum number phase space, okay? And I'm plotting that. Now remember that for your particle in an infinite square well, your energy of the particle is very much dictated by the size of the box that you place it in, okay? So if you restrict it, you're restricting the values of the energies that are available, and that can be shown here, okay? So what we're going to do is we're going to look at the values of n, basically, that are available in this phase space. All right. So first of all, you can think of these particles as being confined not only in physical space, but also with their energies. And that's because of the confinement of the particles to the cube, or whatever else you're sticking it in, okay? When you confine it, that restricts the values of energies that they can hold. Now, also remember that for the infinite square well, the values of our quantum number n started at 1 and went up from there in integer steps, okay? So this means that our values of n can never be negative. So if I were to plot all possible values of my quantum number n, then I would have my nx, my ny plus nz, right? And if you have nx squared plus ny squared plus nz squared is equal to n squared, then you're basically making a sphere, okay? Now, the thing is, it's not an entire sphere. You're only going to get 1/8 of that sphere, right? Because you're only going to get the part of the sphere that's in this quadrant where all values of nx, ny, and nz are positive. And that's just because of the restrictions that we replaced on our quantum number n way back when. They all have to be positive. So this is 1/8 of a sphere, all right? So that explains this factor of 1/8 that's here out front, okay? Now what we're doing is we're looking at just a little slice of our sphere. So we're really looking at a spherical shell, okay? And what we want is the energy states available, or the energy level states available in that shell. So we're looking at a little slice of the shell, which would have some thickness dn, okay? Now, if you wanted to calculate the energy states available, you would calculate the volume of this little slice of spherical shell in phase space, okay? So, remember that for a sphere, the surface area of a sphere is 4 pi r squared. Since here, our sphere is in space, then the surface area of our sphere would be 4 pi n squared, all right? Now, we don't really want an area, we want a volume because we want all the available energy states in there. And so we're going to take 4 pi n squared and multiply it times the thickness of our little shell, which is dn. Okay, so that explains the 4 pi n squared dn that's present in this density of states function. Okay, so we've explained the 1/8, we've explained the 4 pi n squared dn, and now the only thing left is to explain the 2s plus 1 over v. Well, the v here is just the volume. Remember that it's the energy states available per unit volume, so you got to divide by your volume. So that's easy. Now the 2s plus 1 is just the spin states that are available, okay? So remember that for any kind of angular momentum quantum number, be it s, be it l, or whatever, there's m sub s states and m sub l states that are available that run from minus s to plus s, or minus l to plus l, depending on what you're looking at. And that makes the multiplicity there 2s plus 1, okay? So we're including this 2s plus 1 divided by v times 1/8 4 pi n squared dn, and that is our density of states with respect to n. Hopefully that's clear. If it's not, please do go through, rewind and watch it again, or read through the section of your textbook very carefully. Actually, I encourage you to do that anyway. Okay, so what we need to do really is since we want the number density with respect to the energy, then we need to switch our variables. Really, g of n dn is the same as g of e dE because e is directly proportional to n squared. Okay, but we do have to switch our variables. So instead of this function that we've got now, 1/8 2s plus 1 over v 4 pi n squared dn, we need to plug in there and get it as a function of e instead. Now, if we rearrange our equation for relating e and n squared, then we have n squared is equal to 8ml squared e over h squared, okay? And we're going to plug that in for our n squared here in the function. Now, we need to solve for dn, and so if we take the derivative of both sides of that equation for n squared, then we have 2n dn is equal to 8ml squared dE over h squared, okay? Now, because this expression that we have to plug in here for dn also has n in it, then we need to know what n is by itself. And so I take the square root of both sides of my equation for n squared and get that n is equal to L over h times the square root of 8ne. Okay? So now we have this relationship here, and we're going to plug all of these factors back into my density of states, okay? So we have 2n dn. I need to go ahead and plug in for n into that expression so that I just have a straight up relationship between dn and dE that doesn't have another n in it. So I'm plugging in 2L over h times the square root of 8me dn is equal to 8ml squared dE over h squared. And then that gives me dn is equal to 8ml squared dE over 2L over h root 8me h squared. And then if I simplify that further, then I get this little expression here, okay? Now, I'm going to take all that and plug it into my expression for g of n so that I can fully switch my variables over, okay? So here I do that. G of n dn, and I'm plugging in for dn, and I'm plugging in for n squared. And when I do that, I end up with this. 1/8 2s plus 1 over v 4 pi 8ml squared e over h squared square root of 2m over e L over h dE. Okay, so make sure that you can follow the algebra yourself and plug in for that. Okay, now simplifying that expression a little bit, my 8's cancel, some of my other things simplify, and I get 2s plus 1 over v, 4 pi, and then here I have an m outside my square root and then a square root of m. That combines to give me m to the 3/2. And then here I have an l squared and an l. That combines to give l cubed. Here I have an h squared and an h. That combines to give me h cubed here on the denominator. And then here I have e over the square root of e, and that gives me here root 2e. The root 2 comes from the combination of the, oh no, it's just from there, right there. Okay, so there's my expression for g of e. Now, it's also true that we want this to be sort of valid for any shape that we've got. So the volume V of a cube is actually just L cubed. So we can cancel those out. See how L cubed and V, they cancel out. And there's a few other things that can be done to make this expression look a little nicer. For example, here I have, this will be important later in other derivations, but I have m to the 3/2, and then I have h here, okay? So what I can do is I can plug in a c cubed on the top and the bottom, and then I get this expression mc squared to the 3/2 over hc cubed, okay? That'll be relevant and handy later on, so that's why we did it here. Okay, so this is our expression for our density of states for our ideal gas. So there you have it, 2s plus 1, 4 pi, mc squared to the 3/2 over hc cubed times the square root of 2e dE. That's our g of e dE. Now we're going to plug this in to our expression for our number density. Okay, so here n of e dE is our volume times our density of states times our Maxwell-Boltzmann factor. Now the only other thing that we have to maybe explain a little bit, other than that it's very plug and chug, is what this a to the minus 1 here is. This is a normalization constant, okay? Because when you have your number density, if you integrate your number density over all possible energies, you should get the total number of particles that you have. So to force that to happen, we're going to put in this normalization constant and then perform the integration and then solve for what that normalization constant really is. Okay, so that's our strategy here. So I'm putting in this normalization constant. I went with a to the minus 1 to be consistent with your book's notation. So here my number density is a to the minus 1 times my volume, which is from this expression for n of e, times my density of states, g of e, which takes us up through the root 2e there, and then times my Maxwell-Boltzmann distribution function factor, which is that e to the minus e over kt. Okay, so plugged in for everything there. Now, solving for that normalization constant to find a, I just have to integrate that over all possible ranges of energies. This stuff right here is all constant, so I can pull it out front. And then I just have to integrate root 2e, e to the minus e over kt dE. Now, that has to be integrated from 0 to infinity. The reason is I need to integrate over all possible energies. And of course, since they're kinetic energies, these energies cannot be negative. Kinetic energies are not negative. And so there you have it. All right, now from the tables, I can perform this integration here, 0 to infinity, root e, e to the minus e over kt dE. And when I do that from the tables, I get root pi over 2 times kt to 3/2, okay? So you can look that up, perform the integration on your own, prove it to yourself if you like, but that's what doing that integration will give you. Now, if I plug in for that, then I get this expression here. N is equal to a to the minus 1, v, 2s plus 1, 4 pi, mc squared to the 3/2 over hc cubed, root 2, root pi over 2, kt to the 3/2. Okay, so that's kind of a mouthful. But now the whole point of that was just to solve for my normalization constant, a to the minus 1. And so now I can rearrange that expression, solve, and do some simplification. Okay? When I do that simplification, I get that a to the minus 1 is equal to n times hc cubed over v, 2s plus 1, 2 pi mc squared kt to the 3/2 power. All right, kind of a mess, but make sure that you can do that yourself. Now finally, if I plug in for that normalization constant into my expression for my number density, I get this mess right here. Okay, there's some simplifications that take place. There are a lot of things that cancel. The mc squareds cancel, the hc cubes cancel, the v and the 2s plus 1 cancel. Anyway, lots of stuff. Make sure that you understand it, can go through and derive it yourself. But what I end up with is this n of e dE is equal to 2n over root pi, kt to the 3/2, square root of e, e to the minus e over kt dE. Okay? And that's it. That's our expression for the number density for the Maxwell-Boltzmann distribution function. And this is what Maxwell and Boltzmann derived themselves and proved such a success. Now, you can also, because sometimes it's more convenient to do this, write it in terms of the distribution of the speeds of the particles instead of the energies. Sometimes that's handier because you can directly measure particle speeds in your experimental setup. So that's handy. So all you have to do that is do another variable switch. Now I'm not going to go through the algebra of how to do this variable switch, but all you have to do is assume that the energy is equal to the kinetic energy, which is 1/2 mv squared, and switch your variables. Okay? Most of it you can kind of see by glancing at it that this would be the case. You just need to make sure that you've got the constants squared away in your mind that are out front multiplying this stuff. Trust me though, okay? And then prove it to yourself. For now, the number density for the speeds is equal to the total number of particles in times the square root of 2 over pi, m over kt to the 3/2, the speed v squared, e to the minus mv squared over 2 kt. Okay, so that's your distribution for molecular speeds. So what you've got is you've got a decaying exponential, right, that's multiplied times this little polynomial v squared here out front, all right? When you plot that, that looks like this. You can see that for low speeds, the v squared term dominates. And then as the speed gets larger, your e to the minus mv squared over 2 kt term becomes dominant, and then it starts to decay off like an exponential. So you have this increasing, you reach your peak, and then it decays off from there. This is not a symmetric wave function. It's not like a Gaussian or something like that. I'm sorry, it's not a symmetric distribution function. It's not like a Gaussian or something like that. It's something that has a long tail, okay, because the speed must go to 0 here for the particles. Now you can see that because it's asymmetric, there's definitely 3 speeds that you could say that are all going to be different that explain and help describe this distribution function. This VMP here is the most probable speed. To get this most probable speed, what you would do is you would take the derivative of your function n of v dv, you would take that derivative of n of v and set it equal to 0 and solve for your speed. And that'll give you your most probable speed. You can also get your average speed. That'll be to the right or larger than your most probable speed because the distribution function has that long tail. Because it's not symmetric, it gets pulled to the right. Okay, so your average speed, what you do is you take your n of v dv and you integrate it multiplied times v. Okay, so remember those are part of the rules for distribution functions. If you want the average value of something, you take your distribution function and you multiply it times the value of interest, and then you integrate, okay, over all possible values. So that gives you your average. Now, in the previous lecture when we talked about the ideal gas and its classical roots, we showed from first principles physics what the root mean square speed was. And we got that by setting 1/2 mv squared is equal to 3/2 kt using equipartition of energy, and we saw from there. And that's the root mean square speed of your distribution, and that's even to the right of your average speed. So if you look at what the values for all 3 of these quantities are numerically, you get that your root mean square speed is equal to root 3 kt over m. And that your average speed is somewhat lower than your RMS speed. You can prove this by performing the integration, that the average speed is equal to the square root of 8 kt over pi m, right? And then your most probable speed is the peak of that distribution function curve, which you can get by taking the derivative of your distribution function and setting it equal to 0 and solving for v. And that gives you the square root of 2 kt over m, okay? So there's your 3 speeds. And your root mean square speed is larger than your average speed, which is larger than your most probable speed. Now, as you increase the temperature, that's going to change the shape of your distribution function. It's going to pull it to the right, okay? So that's pictured here. You can see the curve for a particular gas, nitrogen in this case, at 300 Kelvin, and then what that same curve looks like at 900 Kelvin, all right? So the peak shifts to the right. The distribution of molecular speeds depends upon both the mass and the temperature, okay? So for the same temperatures, lighter gases, like helium, for example, as compared to nitrogen, the lighter gas will move much faster at the same temperature than the heavier gas, all right? And of course, it depends upon the temperature too. You can use the Maxwell-Boltzmann distribution function to explain a lot of interesting physics. For example, it can help explain evaporation. So what's happening there is, let's say that you have some molecules in your liquid, and you can kind of model a liquid and under certain circumstances using a similar time distribution function. You can assume that some molecules in the liquid are more energetic than others, right? And they have very similar distributions of speeds. And then what happens is some of the faster moving molecules actually penetrate the surface and leave the liquid. And that happens even before the boiling point that is reached. And then those molecules that escape are those that have enough energy to overcome the attractive forces, and then they leave it behind. And so what's happening at evaporation is that you're losing your most energetic or hottest molecules, your hottest particles, and that means that you're going to be cooling the whole substance down. What's left behind is a colder substance than what you started with, because the ones that you're losing are the most energetic, and that helps explain a little bit about evaporation. As an aside, it's also kind of interesting and helps explain why some planets don't have atmospheres. So remember that for a planet, the escape speed is proportional to the mass of the planet. So for lighter planets, you have lower escape speeds. It takes less energy to escape the planet. Well, you can see that if you have this distribution function with this long tail, that for a light planet, sometimes the gases on the planet, depending on the temperature on the planet, might actually be light enough to have an escape speed, right, that's large enough to get out. And so then eventually you're going to lose all the gas on that planet just because the gravitational pull of the planet makes the escape speed low enough that gases at temperatures achieved on the planet can escape. Okay, so that helps explain why some planets have atmospheres and others don't. Okay, so how are we going to use this distribution function that we've got? Well, one typical type problem is to use just the Maxwell-Boltzmann factor, e to the minus e over kt. Apply it to pretty much any classical system, and then tell what the relative probability of the occupation of those states are, all right? So here's an example problem that I'd like to work and show you for that idea. Here you have the energy difference between the first excited state of Mercury and the ground state is 4.86 eV. So that's your delta E between state 2 and state 1. Let's say that you have a sample of mercury gas that's been vaporized in a flame or whatever, and it's got a collection of 10 to the 20th atoms that are in thermal equilibrium at 1600 Kelvin, so it's a very hot gas. Let's calculate the number of atoms in the ground state versus the first excited state, assuming that this collection obeys Maxwell-Boltzmann's distribution function, and that n equal to 1 and n equal to 2 have equal statistical weights. So what we're doing here is we're plugging in for a Maxwell-Boltzmann factor. So the probability that it's in the state 2 versus the probability that's in state 1 is e to the minus delta e over kt. Now, delta E for this system is 4.86 eV. Okay, so that's our delta E, and we plug it in here. Boltzmann's constant in units of eV per Kelvin as opposed to joules per Kelvin is 8.6 times 10 to the minus 5. And then we multiply that times the temperature of the collection, which is 1600 Kelvin. When you plug all this into your calculator, you get the ratio of the probability of state 2 to state 1 is equal to 4.97 times 10 to the minus 16. So what this is telling us is that the probability that the particles are in state 2 relative to state 1 is very, very low. That even at this high temperature of 1600 Kelvin, most of those are going to be in your ground state, all right? So for all intents and purposes, we can assume that since the probability that they're in state 1 is so large that you may as well call it 100% or 1, that this is just the probability of occupation that it's in state 2, this 4.97 times 10 to the minus 16, right? Okay, so that's our probability that it's in state 2, and then we multiply that probability times the number of particles to get the total number of particles that are in the first excited state. So we have 10 to the 20th times 4.97 times 10 to the minus 16, and that gives us 49,700 atoms, which out of a collection of 10 to the 20th atoms is really not all that much, okay? But it is measurable maybe, so there you have it. Okay, so that's the Maxwell-Boltzmann distribution function, an introduction to that, a way that we use that Maxwell-Boltzmann factor to calculate probabilities. I hope you sort of understood that. You might need to watch it a couple of times and go back and make sure that you can do the math.